PDCP is used for both the control plane and the user plane. It is used for all data radio bearers, but only for signaling radio bearers mapped onto the logical channel dedicated control channel. PDCP is not used for broadcast control channel, paging control channel, and common control channel. PDCP provides functions for integrity protection and ciphering for the control plane, only ciphering for the user plane, in-sequence delivery and duplication elimination in case of HO when lower layers need to be re-established in the new cell. Valid for user plane RLC acknowledge mode only. Header compression for the user plane. The PDCP sublayer in eNode B and UE includes one PDCP entity each per signaling radio bearer 1, signaling radio bearer 2, and every data radio bearer, evolved packet system bearer. The PDCP sublayer is configured by the RRC layer. There are three main types of PDCP PDUs. Control plane PDCP data PDU used for delivery of control signaling for which ciphering and integrity protection is provided by PDCP. In case of user data user plane PDCP data PDU is used, for which PDCP provides header compression and ciphering. PDCP control PDU for PDCP control signaling. For signaling concerning the user plane, the maximum PDCP SDU size is 8188 octets. For a PDCP service data unit, proceed from RRC, the UE shall assign a PDCP sequence number, perform integrity protection on the PDCP header and payload, cipher the payload information, including the message authentication code. The integrity protection and ciphering algorithms plus the keys to be used are configured by the RRC layer. It is also the RRC layer that activates the integrity protection and ciphering. The input parameters in the algorithms are the count value, which is based on the hyperframe number and the PDCP sequence number, the value of the radio bearer identity -1, and the direction of the transmission. The output is a control plane PDCP data PDU. The PDCP protocol is symmetric. Here uplink is described, but the functions and procedures applies equally for downlink transmissions. For a PDCP service data unit received from IP, the UE shall assign a PDCP sequence number, perform header compression on the header for the layer above, if configured, cipher the payload information. The ciphering algorithm plus the key for the user plane to be used are configured by the RRC layer. It is also the RRC layer that activates the ciphering. The input parameters in the algorithm are the count value, which is based on the hyperframe number, and the PDCP sequence number, the value of the radio bearer identity -1, and the direction of the transmission. The output is a user plane PDCP data PDU. For the user plane, a PDCP control PDU has also been defined. The control PDU is used in two situations. For transmitting feedback on the header compression, call PDCP control PDU for interspersed ROHC feedback packet. For notifying the transmitter of missed SDUs when the PDCP is re-established. This control PDU is called the PDCP status report and is only valid for the acknowledged mode services. The PDCP protocol is symmetric. Here uplink is described, but the functions and the procedures applies equally for downlink transmission. The security procedure starts with the UE sending up its MC or corresponding ID. From the MC, the MME will derive the user operator HSS. The MC will be signaled to the HSS. Every subscription has its own security key, K, stored and protected within the HSS. Together with a random number, the K will be inserted into an algorithm. The output from the algorithm will be the integrity key, the ciphering key, the response value, and the authentication network. The integrity key and the ciphering key will be put into another algorithm to form the Key Access Security Management Entity. The K-ASME, the RES, the RAND, and the AUTN will be sent to the MME. MME will put the K-ASME into an algorithm to calculate the key for NAS integrity protection and the key for NAS ciphering. MME will also store the RES value. The K-ASME, the RAND, and the AUTN will be passed on to the eNode B. eNode B will put the K-ASME into an algorithm to calculate the key eNode B. The key eNode B will be put into an algorithm in order to calculate the key for RRC integrity protection, RRC ciphering, and user plane ciphering. Sent over the air interface is now the RAND and AUTN. The UE will use the RAND as an input to an algorithm, together with the key K, which is securely stored on the SIM card. The output will be the integrity key, ciphering key, response value, and authentication network. Before the UE takes any further actions, it will compare the received AUTN with the calculated. If the two parameters match, the home network operator is authenticated. From IK and CK, K-ASME can be calculated, and from this parameter, all the other keys for integrity protection and ciphering usage on the UE side of the air interface can be calculated. KNAS for integrity and KRRC for integrity will be put into integrity algorithms. KNAS for encryption, KRRC for encryption, and K user plane for encryption will be put into ciphering algorithms. Please note that none of these keys have been transmitted over the air interface. The UE has calculated them by itself, thus providing a high security level. The UE will answer to the MME with a calculated RES value. MME will compare the RES received by the HSS with the RES from the UE. If they match, the UE is authenticated. Please note that the key K stored in HSS and on the SIM card is never sent anywhere, only parameters derived from them. This is what is handled by PDCP. The purpose of the re-establishment procedure is to reset the radio bearers in the new cell during a handover. The re-establishment differs between the different types of radio bearers. For RLC acknowledge mode bearers, the PDCP sequence number will be maintained. For RLC unacknowledged mode bearers, the transmission in the new cell will just continue, without duplication nor out-of-sequence delivery being taken into account. And for signaling radio bearers, PDCP will be reset from 0 in the new cell. Re-establishment for RLC acknowledged mode radio bearers. The source eNode B will send a sequence number status message including count value and hyperframe number for uplink and downlink for acknowledged mode ERABs requiring re-establishment to the target eNode B. The target eNode B will instruct the UE via the source eNode B to send a status report by sending the RRC connection reconfiguration request with the status report required included. The UE resets the header compression and applies the ciphering algorithm and key both for the uplink and downlink. The information about the ciphering algorithm and the key to use is provided by the RRC layer. The UE continues with re-establishing the lower layers and then processing the PDUs received from the lower layers. The UE shall then compile a status report. The FMS field is the PDCP sequence number for the first missing PDCP service data unit, in the example sequence number 4. In the bytemap field, the UE shall indicate for each following SDU if it is missing or not. Each SDU is indicated only with one bit, and the first bit in the bitmap holds the information about the next SDU following the first missed. The second bit holds information about the second SDU following after the first missed, and so on. If the bit is set to 1, the SDUs have been correctly received. If it is set to 0, then the SDUs are missing. In the example number 6, 7, 9, and 11 are missing. The target eNode B will then transmit the missing SDUs. The target eNode B will compile a status report for the uplink missing SDUs, and the UE will retransmit them. The retransmitted SDUs will be sent with a new header compression and ciphering configuration established in the new cell. Re-establishment for RLC unacknowledged mode radio bearers. For unacknowledged mode ERABs requiring re-establishment, the UE resets the header compression and applies the ciphering algorithm and key, both for the uplink and downlink. The information about the ciphering algorithm and the key to use is provided by the RRC layer. Continue the transmission of SDUs from the point it was interrupted by the re-establishment. Re-establishment for signaling radio bearers. When upper layers request a PDCP re-establishment for signaling radio bearers, the UE shall discard all stored service data units and protocol data units within its buffer. Apply the ciphering and integrity algorithms and keys. The information about algorithms and keys to use is provided by the RRC layer. The UE shall also discard all PDUs received from lower layers due to the re-establishment. Set the sequence number both for downlink and uplink to 0. The header compression function of PDCP is using the robust header compression ROHC protocol defined by IETF. The header compression is a method of squeezing down the information in the IP header and headers following above IP. The reason for using this method is to save bits on the radio interface, especially for real-time service applications like, for example, voice over IP, where the header information is unproportionately large compared to the payload. The IP header for IP version 4 is 20 bytes and for IP version 6, 40 bytes. The typical payload size for sample voice is around 30 bytes. There are multiple header compression algorithms called profiles. Each profile is specific for the network layer, transport layer, and upper layer combination, like the profile for RTP, UDP, IP compression, TCP, IP compression, and only IP compression. Which profile to use for each radio bearer is configured by RRC during the setup of the service. Out from the compression protocol, there are two types of packets. Compressed packets associated with a PDCP SDU, standalone packets not associated with a PDCP SDU nor a PDCP sequence number. These are called interspersed ROHC feedback packets. The interspersed ROHC feedback packets are not ciphered. The header of the PDCP data PDU for the control plane consists of 3 reserved bits and a sequence number of 5 bits. In the end of the PDU, the message authentication code is added for integrity protection. The header of the PDCP data PDU for the user plane consists of 1 bit for indicating if it is data or control. If data, the bit is set to 1. 3 reserved bits and a sequence number of 7 or 12 bits. The length of the sequence number is configured by the RRC layer. 7 bits are used for unacknowledged mode on the RLC. 12 bits are used for both unacknowledged mode and acknowledged mode on the RLC. With the long sequence number, 3 bits in the header are reserved. For the user plane, a PDCP control PDU is defined. The control PDU is used in 2 situations. For transmitting feedback on the header compression, called PDCP control PDU for interspersed ROHC feedback packet. This PDCP control PDU is not ciphered nor integrity protected. Integrity protection is applicable only for the control plane. For notifying the transmitter of missed SDUs when the PDCP is re-established. This control PDU is called the PDCP status report and is only valid for acknowledged mode services. The PDCP control PDU for interspersed ROHC feedback packet is used for transmitting feedback for the header compression. The control bit is set to 0 to indicate control. The next field of 3 bits indicates the usage of the control PDU for ROHC feedback. The bits are set to 001. 4 bits in the header are reserved. The PDCP status report indicates which PDCP SDUs are missing and which are not after a PDCP re-establishment during a handover. The status report is only applicable if RLC AM bearers are about to be re-established. The header for the PDCP control PDU used for status report includes the field indicating data or control set to 0. The PDU type field is set to 000. The next field is 12 bits long and indicates the sequence number of the first missing PDCP SDU. The next field, called the bitmap, indicates the missing SDUs after the first one. Each SDU is indicated with only 1 bit. The first bit in the bitmap indicates if the first SDU after the missing one is received correctly or not. The second bit in the bitmap indicates if the second SDU after the missing one is received correctly or not, and so on. If the bit is set to 0, the SDU is missing. If it is set to 1, the SDU has been correctly received. Please notice that PDCP control PDUs are not ciphered nor integrity checked.